Okie dokie. Right, so in the last Python Club, we were starting on a design of experiments type series. So I did an experiment in the lab with a 96 weld plate as a sort of pilot study. So the aim of this section or season, let's call it, of Python Club, we're going to look into optimal experiment design, and we're going to try and see if a standard E. coli growth media is actually optimum, and see if we can optimize it a little bit further. And if we can't, that's okay. It's more as a sort of introduction to experimental design and so on. So we'll be measuring the response of E. coli as growth rate by fitting the Gompers equations, which Steve has got a pretty thorough equation tutorial for, which I've linked up here. And there's a nice review here that goes into a little bit more detail of why and what variants people use. So based around this sort of structure, but we'll delve more into that in a little bit. So section 1, we did an initial experiment. It was a plate reader experiment where every other row in this 96 weld plate was bacteria, or E. coli DH5 alpha in LB, the lysogeny broth, and every other well apart from those was just the broth itself as like a zeroing. So we did some preliminary analysis, and we almost had time to calculate the growth rate for each one, but not quite. In this session, we're going to design a round of experiments and finish up what we started from last time. And then next week on Friday, I will try and do these experiments, and then we could analyze them again, but we've already made some functions to sort of automate the analysis, so that should be pretty quick. Then we can get straight to fitting a model, designing another round of experiments, and hopefully finding something pretty close to the true optimum, at least within the experimental space that we're looking at. Okay, so we had a data frame, and we did some cleaning and managed to put the well IDs as the index and the timestamps as the columns. We use a little bit of regular expression to turn those 0h15 mins sort of timestamps into numbers in minutes, which is handy. And we started to look at plotting. Let me connect this runtime and run all of these cells. Okay, so what I hope would happen was I'd be able to see. Okay, so here's the problem. Expected as strings or oh no, this is a bummer. So I was kind of hoping that I'd be able to dive straight into the first exercise, but no. So what's the problem? Let's have a look at df.columns in the cell above and try and debug this problem. Okay, so in this specific instance, I think what happened was that I had already processed or already set the columns as, or run these cells, set them as integers, and then tried to run those integers through the processing function again, which expects strings. I think that was the problem there. Maybe a result of me running the same cell twice. Yeah, let me know if you have a similar problem. Okay, I changed the data type of the contents of the data frame because by default it's a string for some reason. And we made a quick plotting function. I think we didn't quite get enough time last time to get as far as making this quick plotting function. But in the answers file, I do have a quick plotting function. And on purpose, I took out the legends because the legends have 96 labels in, which would have sort of taken up the whole page and been pretty unreadable. So this is the sort of data we have. Here are the controls with the optical density at 600 nanometers at each of these time points, and the sort of sigmoid curves, that's the bacterial growth curve. There's a few anomalies here and there, like for example, after about 5 hours, there's a pretty strange dip in all traces in at least the LB bunch, which I haven't thought of an explanation for yet. Another sort of strangity in the data is sort of obscured by the baselines, but it'll become relevant later. So rather than sort of behaving like a normal sigmoid curve where it goes flat then up, these bacterial growth curves go down then up, which is a problem, but we'll come on to why next time. Okay, session 2. So the aim of this session is to calculate the growth rate for each experiment. We'll do that by fitting the Gompertz equation, the Gompertz curve, to our data, and then extract the parameters from that. We will identify some issues in the experimental procedure because there are issues, and then we'll design the next round of experiments. Topics we'll cover are a little bit more of SciPy curve fit, where this time we'll be using upper and lower bounds like we did in the past. We'll look briefly at subplots, which are a pretty useful aspect of matplotlib. It's a way to sort of have a nice big grid of images. And we'll look very quickly at DexPy, which is a design of experiments in Python package. Design of experiments being a pretty generic name for optimal experiment design, or at least some methods of that. And then we'll use that to design the next round of experiments, which I'll do next week. Okay, so the variant of the Gompertz equation that we'll use today is this. WT being the growth, or the amount of biomass, or however you want to quantify growth. In our case, it's going to be the OD 600, is equal to WM, a constant that is the sort of the maximum population growth. So that will be where the curve will flatten out, times the exponent of the negative exponent of minus. I'm doing a bad job at saying this equation out loud, but in short, the aim of the exercise is to write a function that gives us WT for a given set of parameters. So I've already started writing a function in here that takes in WM, the sort of upper asymptote, the maximum population size of our E. coli and their wells, which will be determined by the amount of bacterial broth in there, basically the amount of LB in there. TM, which is the time that the growth curve goes from going up to sort of plateauing off. That's called the inflection point. K, the growth rate, and T, the time point at each particular time. I've left a clue if you don't already know how to make an exponent in Python. One of the simplest ways is to use numpy.exp. I'll give us 3 minutes to do that, because that's hopefully a quick one. And in the meantime, it'll give me a little bit of time to start drawing Christina's World by Andrew Wyeth. I'll see how this one goes. Have I set the timer? Yes. Okie dokie. I hope we all got on okay with that. So let me start filling in the blanks. So I'll create a temporary variable, WT, and then we can sort of have our function return that at the end. So we'll have WT equal to WM times MP dot exponential, and we'll take the exponential of minus NP dot exponential of minus K times T minus TM. Return WT. That looks okay to me. Let's try it out. Let's make some X data. And let's set that equal to range 100 minutes, and Y will be equal to Gompertz. So to map the Gompertz function to each variable or each item in this range object, I think the easiest way to do that is with a list comprehension. Mapping functions to iterables is easy enough if the function only takes in one variable, but it gets a little bit more difficult when it takes in more than one variable. So for now, we will just go for, what should we set WM equal to 1, TM, let's set that to 50, so the inflection point will be sort of halfway through the range, and the maximum growth capacity will be 1, so it should plateau out at 1. What else? K, let's put that equal to something quite small, 0.0001. And T will be each item in this range object. PLT dot plot T temp and Y temp. That will throw an error. So will that. PLT dot show. A positional argument follows a keyword argument. Let's try this. Okie dokie. What might I've done here? Let's bring up the growth rate a little bit. Maybe it'll start to make more sense. There we go. Okay. So the reason why it was a straight line before was because it was such a slow growth rate. But we can see that WM, the maximum of the asymptote, is 1. TM, where the inflection point where the curve starts to change direction, is about 50. And this growth rate K, we can play with a little bit. We can make it slightly sharper and so on. Okay, cool. I thought I'd put in a little cell with some random parameterizations of the Gompertz plot so we can sort of get a feel for the different parameters. And also it sort of is a very brief introduction to subplots, which, like I mentioned earlier, are sort of grids within your figure, within your plot. Which is pretty useful if you want to say compare lots of pieces of data, which we will do later on, or if you want to have a figure that in itself contains several plots. So, like for example, for our UV vis data analysis, it might be good to have separate or subplots of the spec itself and then the curve fit and so on, all in one object. Short of actually going through the code that I've put in here, in each loop, and it loops over 5 times, the parameters WM, TM, and K are picked randomly from uniform distributions within these ranges, which for a bit of trial and error, I thought looked vaguely sensible. And I've plotted in the dotted lines which show where the inflection point is and where the maximum asymptote is. And then from that, we can sort of get a feel for what the growth rate actually means as well. Okay, subplots. A really nice explanation of subplots are in the Python Data Science Handbook, specifically in Chapter 4 under this link here. It's a free ebook and I very highly recommend it. The standard syntax that I use, although there are multiple ways of doing it, are to initialize a little bit like this. Fig and ax are equal to plt subplots and then the arguments. So plt.subplots will return two objects, one figure object, which I find I don't interact with very much, but it's the sort of basic class for plots and objects and so on. And more importantly, ax, which is typically a NumPy array that contains references to each of the subplots within the figure. So for example, if I say number of rows is 2, number of columns is 2, then ax will be a 2 by 2 NumPy array, and I can access each of the subplots by slicing that NumPy array to find one specific element and then say to that element, plot this, plot that, title this, and so on. I was going to make a cheat sheet that I ran out of time. Maybe I'll remember to come back to that. Apologies. Okay. Yeah, here's an example of the object class of each element within the NumPy subplots array, the NumPy array of pyplot subplots, I should say. We can plot pretty much whatever we want on those. It's just as flexible as any other plotting method in matplotlib. The commands for the aesthetic changes differ very slightly. So for example, whilst the plot commands or scatter or hist or whatever you might be using are the same on the whole, for the aesthetic changes, typically they're preceded by set and underscore, like for example, set title or set y-axis or other aesthetic changes that you might care to think of. Which brings us on to exercise 2.2. So below, I've started making a pair of subplots. So you can see I've initialized this pair of subplots with plt.subplots, 1 row, 2 columns, and I've explicitly put in a figure size because I find when I don't do this, they can quite quickly become quite squished because it'll just try and squeeze all of your subplots within the default figure size, which is maybe 5'5", something like that. I've made an x-axis, it's integers between -10 and 10, and in the first plot, the first subplot, I've accessed it from this array ax, which I'll show you up here, using standard slicing. So it's only a one-dimensional array. So I only need to use one number, but say I'd specified a two-dimensional array, then comma. Yeah, let's make it less busy. So to access items in a two-dimensional array, then I might want to use two-dimensional slicing like this, and so on. Okay, let me delete this cell. I specified the y for this plot within the cell. It's x squared, pretty much. I did that again with a list comprehension. Your exercise is to plot y equals the exponent of x on the second subplot, and add the aesthetic changes like a title, axis, and axes labels. I will set a 3-minute timer again and get back to Christina's world. All the colors in this are quite muted, so it'll be a fun chance to play with some of these muted colors. Whatever. Okie dokie. So the scope of the exercise was to plot y equals e to the power x on the second subplot. So I will start by making y temp, TMP for temporary, because I can't remember if I already saved a variable as y, but I'll put temp on the end so that I know it's okay to overwrite it. Y is equal to numpy.exp I for I in x axis. Okie dokie. So that's our y variable there. We have our x-axis here. So now we'll be wanting to access x1 and plot x-axis and y temp. Let's see what that looks like. Okay, that's good. Now all we need to do is to add the aesthetic or cosmetic changes. So dot set title. What did I say it was? Y equals e to the power x. X1 dot set y label y yeah, you get the idea. X label would have been the same, only with X in there instead. Cool. Okay, moving on. So in this cell, I have created a variable called X. Why did I call it X? I think because I wanted something that was as few keystrokes as possible, and DF was already taken, so I decided X. But it's not a very descriptive name for what the variable contains, so I suppose it's not necessarily the best thing to call it. But what is X? It's the data frame with the first column subtracted from every single other column. So I've essentially zeroed everything to the first reading. Specified axis equals 0 so that it will be subtracted along the columns. What I've also done is located every other row. Every other row in the data frame corresponds to every other column in the plate, where columns in the plate are numbered 1, 2, 3, and so on, and rows are letters A through H, I think. And the way I did the plate was the first row had, I think, cells in. No, the first row had just buffer in, just media in, LB by itself, and then the second row had media with cells, and so on. So if I get everything in row 2, 4, 6, 8, and 10, and so on, then I have only cells. So that's why I've done that, and now we can start working with this variable X and start curve fitting. So we've done curve fitting before, and in this section it doesn't quite go to plan, but we'll see how it goes. So an important thing to know about with curve fitting are setting bounds, upper and lower limits of each of the variables. It's especially important if the different variables are on different orders of magnitude to each other, which in our case is true because K, the growth rate, is typically a few orders of magnitudes less than 1. Yeah, this cell illustrates why it might be necessary. So like we've covered before, I import curve fit from SciPy Optimize, and I feed curve fit the function, which I've taken from the answers file, the Gompertz equation answer, and the X and Y data. So that's the minimum parameters that this function will take, and it returns 2 items, an array of parameters and the covariance matrix. I unpack those 3 items from the parameters list, and then I print them, and they should all be positive. Remember, WM is the maximum sort of amount of biomass, or the maximum OD in our case, which should be above 1, but it isn't. And TM, the time of inflection, should be, well, it should be more than 1, because we know that the inflection didn't happen after 1 minute. We didn't even have our second measurement after 1 minute. And growth rate we've seen typically is way below 1. So this is an example of why it can be important to set bounds. Otherwise, the optimization algorithm might have a bit of a hard time finding the true optimum. That being said, I did have a bit of trouble here, so I'll talk about setting bounds in SciPy Optimize, and then I'll go through what I've done and why it might have failed, and then we can use that last 15 or so minutes to talk about designing the next round of experiments. So I've created a bounds variable. It's a tuple that is a set of items separated by commas within round parentheses, and that tuple contains 2 more tuples, which are corresponding to the lower on the left and upper bounds of each of the variables or each of the parameters for this Gompertz equation. And it's position specific. So 0.6 and 1.3 correspond to the the lower and upper bounds of the first variable that goes into this function, WM. Same for TM, the second one. So I've set the upper and lower bounds as 100 and 300 after a little bit of trial and error. And the growth rate, again, after some trial and error, I set it to a lower bound of 0.00001 and 0.02. And then I feed it into the curve fit equation with the key name bounds. Bounds equals bounds, and luckily it doesn't mind too much if you reuse the sort of the keyword as a variable, which is pretty handy. Again, I unpack the parameters like you would. And then that's how I go about the curve fitting. What I've done below is separate from this first example. So I create a set of subplots with 48 cells, 12 by 8, or 4 rows, 4 columns, 12 rows. And I set a figure size that, after a little bit of trial and error, looked about right. It didn't squish everything. And then I start a loop. I loop over 2 things. The index of X, so that is every well that contained these bacteria for growth. And then the flattened version of X. So the reason I had to flatten it was because if you iterate over a 2-dimensional NumPy array, instead of iterating through each individual item, which is what I want, instead it will iterate over, say, just rows. Okay, my runtime is disconnected, so I'm gonna run all. Okay, yeah, I'm just going to ignore that for now. I feel like I might have had the same problem at the beginning of the session. What's the problem here? Okay. So the problem here is I haven't actually run all of the cells. So at this point, the column headers are still in this format. So that was a change that I'd made in this version of the notebook earlier. Hopefully in yours, it's not a problem. See how we go there. Okay, so we got as far as curve fitting, and now we're back on this cell. Okay, so I'm iterating through the flattened version of X, the NumPy array that contains references to each of the subplots, and by flattening it, it lets me iterate through each individual item rather than iterating through individual rows. In each step, I fit the curve to get parameters and a covariance matrix, which I don't actually use in this case, setting bounds each time. I extract the parameters, I make a subplot, or at least I address the subplot from the flattened X, and I say plot x.columns, which is the timestamps in integers, and the row in question, which is the raw data. And then I plot that against the predicted curves according to these parameters that we derived from the curve fit. We set a title equal to the row, and we also add text, which contains a formatted version of each of the variables, WM, TM, and K. Let's have a look at how that goes. It might take just a second to run, because mostly because of the rendering, I suppose takes the longest. Here we go. So yeah, like I mentioned earlier, it didn't go quite to plan. My sneaking suspicion is that this initial dip in OD that I can't quite explain, but seems to be fairly common in this experiment, might have thrown off the curve fitting and made it difficult to fit the parameters. It's problematic, but I think with the curve fit that we have, the gradient at the steepest point is, in some cases, it's not too far off, or at least by visual inspection, it doesn't seem too far off what we see in the data, but by no means is it perfect. But it's okay, it was just a pilot run, and this is exactly what pilot runs are for identifying issues and bugs and so on. So for the next round of experiments, I suppose I'll need to find out what this initial dip in OD was from the 0 point and address that. But yeah, it seems to be fairly ubiquitous, but typically no, this is strange. It looks like I get the same parameters every single time. Maybe then I've just actually made a stupid error. I'm not sure. Well, hopefully I'll have this figured out by next time. But in the meantime, let's skip on to design of experiments. I've left a link to the Wikipedia article on it here. It's a method for optimal experiment design. So by optimum, we mean getting the most possible information with the fewest possible experiments. And it's particularly applicable when you are testing multiple factors against each other for various pairwise and higher level interactions. It's much more efficient than testing one factor at a time, which will largely ignore interactions between all of the other factors. It makes it pretty well suited for optimization type experiments. But as an initial set of experiments, we'll start with what's called a screening experiment, which takes a fairly large number of factors and then tries to trim that down to the minimum possible number of experiments so that we can at least rule out some factors that probably aren't important, so that our subsequent rounds of experiments can be more detailed but with fewer factors, so it still cuts down the experimental space and we can still hopefully find the global optimum. So the experiment that we'll design today is a screening design experiment, and it will take in a number of factors, 5 this time, because I had a look at how many experiments I'd have to do if I was doing much more than that, and it starts to get quite large quite quickly. So the screening design experiment is mostly to identify the main factors or the most important factors from the list of factors that we give it. So from looking at a few standard bacterial media recipes from openwetware.com, some of the most common ingredients in these bacterial growth media with typical values are tryptone, which contains various peptides, yeast extract, which is Marmite, I suppose, and I guess contains all sorts of nutrients, glycerol, a source of carbon, salt, and glucose. I expect glucose will have a pretty positive effect on overall bacterial growth, but I suppose it's not in all bacterial growth media because it does have some secondary effects that we'll cover another time. To design these experiments, I chose initially to use this module called DexPy, Design of Experiments Python. It's a module for DOE. I've left links to its documentation and its source code. And you can install it via pip, which in this Colab notebook, I've got a command line command there. Okay, so let's jump to designing the experiment. So as far as screening experiments go, yeah, the documentation points us towards factorial experiments with highs and lows of each of the factors. So in our case, that will be zeros and these typical values that I found from Open Wetware. And it will be various combinations of those. So we could have every combination of high and low for every factor, which at 2 levels would be 2 to the 5, which means I'd have to make an autoclave 32 bottles of media, which will be difficult and annoying. So I'm keen to cut down the experimental design space by using a fractional factorial design, which is designed to give us similar information, but with far fewer runs. It's based on the assumption of the sparsity of effects, which basically says that the chances are that there aren't that many pairwise interactions or higher level interactions between the factors in our experiments. Based on that assumption, we can test various combinations and still try and treat the factors sort of individually. This hasn't been an excellent explanation, and I think it probably reflects my pretty suboptimal understanding of it. So sorry for that, but next week I'll have a slightly better understanding. Okay, how do we formulate that? So the number of experiments that we'd have to do is equal to the number of levels, which in our case is going to be 2 for everything, high and low, to the power of the number of factors, 5, minus this constant p. What's p? P is the number of interaction effects that will be obscured by our minimal design. So in our case, if p is 2, then 2 of the factors will be slightly obscured, at least in terms of their interaction by our design. Obscured in the sense that any model that we fit to it, we won't be able to say for sure whether or not they're interacting, I think. I'll do some reading before next week. But either way, with this sort of design, the number of experiments that we have to do is 8, which for something that in theory gives us similar information to the 32 experiment set is very appealing. That's only 1/4. So under here, we install DexPy via pip and then import the Factorial module from it. Something funny that I found with DexPy was you couldn't really do import DexPy and then go DexPy.Factorial, and I don't know why that is. But I'd like to know. Maybe at the end, Steve, I'll show you their source code, and where is it? Yeah, we can figure it out there. But instead, you have to from DexPy specifically import this module Factorial. So to build a full factorial, which is every combination of high and low for every factor, the function is factorial.build full factorial. More information can be found in the documentation, which I've linked to up here. And we have this experimental design, which is factorial.build factorial. We have the number of factors and the number of runs. Number of runs has to be a power of 2 in this case, at least according to the documentation, and it returns us a table that's sort of like a template for our experiment, where -1 signifies the low of each of your factors and +1 signifies the high. So it's various combinations of low and high of, say, tryptone and glucose and yeast extract and salt and so on. So exercise 2.3 is to use this dictionary that encodes the lows and highs of each variable and use that to replace both the columns and the ones and minus ones of this table exbd, and then I can use that next week to make 8 buffers, test all 8 buffers, hopefully iron out the issues that I was having before with this experiment, and then we can analyze the data using the functions that we wrote before, fit a model, and then find out which factors contribute the most or the least to bacterial growth in this case. And then we can start to design the next round of experiments. So this exercise is primarily a dictionary matching exercise. How you do it is up to you. I'll give you 5 minutes to do it. And I'll return to Christina's world. There we go. Let's see. Okay, that's probably the end of the timer, so let's figure out how to do this. I think I'm going to write it in the form of a function. Def fill design. Yeah, why not? Spell right. And yeah, I really need to get better at naming variables. Okay, fill design. Okay, so in its current form, it just returns whatever you feed to it. So I'll be working with this variable ex, and I'll set its columns as equal to levels.keys. That's the dictionary keys that we have here. Pandas doesn't allow columns to be created via a new attribute name.
You spelled columns wrong again.
Ah, thanks, Steve. Yeah, I think I've got a problem with the spelling of columns. Okay, there we go. So the columns are now named like that. Now I think Pandas has a function called replace. Let me check on Google. If in doubt, always Google dataframe.replace. Brill. Okay. To replace. Okay, so what I think I'm going to do is loop through each of these columns and then replace the ones and minus ones with each of the values, hopefully before I completely run out of battery. For column in x.co autocomplete. Perfect. Okay. So I'm going to locate that column. Ex dot. I think I can just locate it with a shorthand like that. Is equal to, and I'll set it equal to itself, but with replace 1 with. Let's replace it with a test value a. Okay, that's good. That's working so far. So now all I need to do is, so the column names I can also use to access this dictionary. So it'll be levels accessed by the column name, and then that will return me the second dictionary nested inside it. And I want to replace the ones with the high value. And I'll copy and paste this line and replace the -1 with the low value. What have I done here? Why is it filling it with zeros and A's?
You changed it when you tried out the test.
Oh, no. Okay, well, in that case, I will remake it in this cell. Thanks, Steve. Okay, there we go. Cool. So in the week, I will make all of these growth media and I'll run the assay, maybe identify the bugs, and hopefully the data will make enough sense so that we can at least fit a model and estimate the importance or unimportance of some of these factors. Yeah, so a question that I had, give me a sec whilst I find my charger. So the question I had was for you, Steve. I was wondering if you had any insights into the import issue with importing different items from dexpy. So for example, I couldn't run import dexpy and then access dexpy.factorial. Whereas if I explicitly import that module, then it does work. So
I think it's to do with whether it's a package within a package or a module within a package.
Okay, so in this case, I think, as I understand it, a module refers to each one of these Python files.
That's right.
Is that right?
Yes.
And the init.py signifies that this whole folder is a package, I think.
I think from Python 3 onwards, you don't need the init. It just needs to be a folder. Unless you have something specific you want to initialize, you don't need it.
Okay. So I wonder why then.
They might keep that out of habit.
Yeah, I think in so when I've been trying to make this enzyme docking, folding, whatever package, I've been putting init.py in there because some tutorials told me to. But if it's not necessary in Python 3, then I think I'll pretty gladly stop using that. Okay.
Yeah, I'm pretty sure it's from Python 3 onwards, so you could omit that.
Ah, that's interesting. Okay.
So
I'll stop the recording there.